Alright, so 5.3 lesson, we're doing integrals and eventually antiderivatives. We're going through some of the rules for definite integrals. This is in your book. The first rule is saying if I'm going from B to A, which is unusual, usually we go from A to B, we can make it A to B, but we just make it negative. So an example of that, if I'm trying to find the area from A to B under the curve, let's say this area is 10. If I went from B to A of our function, well then it would just be the same as from A to B, but it would be negative. So our answer would be negative 10. So if you want to switch these around, you can. It just becomes negative. So if we're accumulating area to the right, going from A to B, we get a positive area if it's above the x-axis. If we're going from B to A, from B to A, we're going backwards, going left, above the x-axis is actually a negative area. It would be negative 10. So that's the first rule. Second rule, if we integrate from A to A, the integral from A to A of anything, you're always going to get 0. Makes sense that we're going from A to A, you'll get 0. It could be 10 to 10, 2 to 2, you're always going to get 0. Third one, constant multiple, we've talked about that. So if we have an integral, this is all on page 269. I'm not taking very good notes, I'm just showing you examples. So let's say I have 4 times x minus 3 cubed dx from 1 to 8. If that 4 is not helpful, well usually it isn't, I'm going to take that 4 out. And then you can just evaluate the rest of the integral and then multiply by 4 afterwards. So you can pull out any constants. You can pull out a negative. It was just a negative f of x here. You could pull that out and it becomes negative on the outside, just like taking out a negative 1. If you have 2 different terms, so if I have integral of x squared plus 4x dx, common sense prevails here. That is the same as integrating x squared from 1 to 4 plus integral of 4x from 1 to 4. You can separate them. So additivity, if we integrate from A to B plus B to C, that's the same as A to C. So back to my little drawing here. Let's say there's a C in the middle. So integral of f of x from A to C to B, well, that's equal to the integral from A to B, which kind of makes sense. If you add this area plus this area, it gets you the whole area. Max-min inequality. Yeah, I'm going to have to talk about that one more. There's a couple examples in your assignment. This is the max-min inequality. Okay, so I think it's helpful to look at the graphical approach. So if I have a function that looks like this, okay, so if I wanted to create an inequality for the integral from A to B, so the integral from A to B of this function f, if you have to do a max-min inequality, we put the integral in the middle, and it's got to be greater than or equal to something, and it's got to be less than or equal to something. Okay, so what is it guaranteed to be greater than or equal to? Well, if we looked at this function and found its minimum is this height right here. That's its minimum. If it was the minimum amount the entire time, it would find that for an area. Like if the y value was the minimum amount, in the whole interval from A to B, well, the function underneath the curve is definitely going to be greater than or equal to that. Okay? So the area under the curve is going to be bigger or equal than if it were the minimum value the entire time. So it would be greater than or equal to the minimum times b minus a. So it's like that distance times the height gives you the rectangle. Yeah, the area under the curve has to be bigger than or equal to that. Okay, the other way is if it was the maximum amount the entire time. Here's my maximum. And let's say it was the maximum the entire time in the interval. Well, that's going to create this big area. Well, the function underneath the original curve is for sure not going to be bigger than that. It's going to be less than or equal to that. It might be equal it, but it's not going to be bigger than it. So it's less than or equal to the maximum times b minus a. And that's the Max-Min inequality in general terms. Questions on that? I'll do it like an example. All right. So maybe the example will help too. So let's say we're going to do, I won't even make it, I'll make it nice and easy. So from 1 to 5, I'll even use kind of the same shape I just did. So that's clearly 2. And the max value, well, that's definitely 6. Okay, so let's create a max-min inequality for this function f of x from 1 to 5. Well, its area underneath the curve, this area right here, and that area, integral f of x dx from 1 to 5, it has to be greater than or equal to something and less than or equal to something. Okay, so if I was going to say it's got to be greater than or equal to something, we need to find its minimum value. Minimum value is 2. So it's going to be bigger than this rectangle. Well, that's our minimum 2 times this width at the bottom, which is 5 minus 1, or 4. So it's got to be bigger than or equal to 8. And it's got to be less than or equal to, if it was the maximum value the whole time right here, it's got to be bigger or less than or equal to that rectangle, which is our maximum, 6 times b minus a, which is 4. Oops, 6 times b minus 4, so that's 24. And that would be your Max-Min inequality. Okay, questions on that? There's a couple. So the problems, if I remember right, I think might be 2 problems in the book. I don't like either of them because I feel like their maximum is 1. So they don't, or the b minus a, this right here is 1. So they don't even, students might not even know to multiply by b minus a here. They just find the maximum and put it right there, and the minimum and put it right here, and you don't even know what you're doing. So remember that you are multiplying the maximum times b minus a, even though in the book you don't even have to. Okay, more stuff. Oh, we got to generate an integral. So I'll just go for my notes. I handed out these notes. I'll go a little bit quicker. So evaluate the integral on a calculator. We learned how to do that yesterday. So we're integrating this parabola from -1 to 3. So it's the area underneath, between the, when I say area under the curve, it's actually the area between the curve and the x-axis. So between the curve and the x-axis, and then between the curve and the x-axis, total looks like you get 5.33 just on our calculator. Okay, so what do you think the mean value? The mean value, you just add it all up and divide by how many there are. Well, if we have 5.3. My mean value is 5.33. Over how many they are, we're going from -1 to 3. So B minus A is 4. It's having a hard time keeping up. So the area under the curve for B minus A gives you 1.33. If you want to find the average value, find the area, divide by B minus A. And we get 1.33. Okay, you'll have to do that quite a few times this year. If you're finding the average amount, you find the area, like evaluate the integral, and then just divide by B minus A. Now there's a mean value theorem for integrals we don't talk a whole lot about. But if you remember the mean value theorem for derivatives, there has to be a point where the average is equal to the instantaneous. So here the average was 1.33. There had to have been a point on this graph where it actually is the function is 1.33, and it goes through the point 1.33 like right there. There has to be a point where the function hits the average, which is the case. We are not going to spend a mean value theorem for integrals. But the average part is something that we're going to need to know how to do. And I can do other examples. That was a little bit confusing, blurry, going back from one thing to the next. Okay, so if I'm just going to talk a little bit about where an integral comes from. If the area underneath the function is capital F of x, that's consistent with this book, other books. Function here, then the area underneath the curve is capital F of x. Okay, so if I wanted to add just a little bit more to it, that's your change in capital F of x. That's your change. Like we're adding just a little bit more, that amount, that would be your change in capital F of x. Okay, your change in area. Well, how do I find the dimensions of that delta capital F of x? Well, the bottom is just your change in x. That's how wide the rectangle is. And your height is F of x. So base times our height. So then we can say that base times height, I'll do F of x, is equal to delta capital F of x. Okay, that's that little rectangle, or the skinny one. Okay, if I solve for F of x by dividing by delta x, then we have F of x equals delta capital F of x over delta x. And therein tells you that the function f is equal to the change in x. While in calculus we'd say f of x equals d capital F dx. So what does that tell you? That if you find the derivative, the area under the curve, you will get the function itself. And then you can say the opposite. If I find the antiderivative of the function itself, you'll get the area under the curve. Okay, so if we have an integral, or if we have a function, if we want to find the area under the curve, it is the antiderivative. That's one way to kind of represent where that comes from. So as far as our whole sequence goes, if I have like f of x, and I wanted to find its derivative, that's f prime of x, find its derivative, f double prime of x, and so on. If we want to go backwards, going backwards from f of x, you will get capital F of x. That's like the antiderivative of f of x. I don't know what the antiderivative of capital F of, maybe it'd be block f. I'm making it up now. Yeah, we'll have to come up, we're gonna have to prove that one. Not sure that holds up. You've seen that before? Yeah. I just thought of it, so yeah. Okay, so let's go back. We're going to use actually apply. I've got a few things in our notes that are not going to be that helpful right now. I may or may not go back and kind of do some proofs. But if you remember, we did an exploration yesterday that talked about the integral of sine x from 0 to pi. Do you remember what that answer was? Remember that exploration? We assumed it to be true. What was this area? Not one person remembers? 2! You're that or you're saying peace, dude. Good. So let's see if we can do that using antiderivatives, and it's called the fundamental theorem of calculus. So what is the antiderivative of sine x? What do you have to take the derivative of to get sine x? Sine x is negative cosine x. So I'm going to write negative cosine x. The integral goes away. We have found the antiderivative. We're going to evaluate the antiderivative from 0 to pi. Okay, so what that means is we're going to drop in our pi, so it's going to be negative cosine of pi minus negative cosine of 0. Okay, so we do the antiderivative evaluated at here minus the antiderivative evaluated at here. So negative cosine, well, cosine of pi is negative 1. So the opposite of negative 1 is 1, plus the cosine of 0 is 1. So we get 2 for an answer. Okay, so I should have started with more general terms. If I evaluate integral of f of x dx from a to b, that is equal to capital F of b minus capital F of a. And that's integrals. You find the antiderivative of it, plug in the top, minus the antiderivative at the bottom. That's a capital. All right, questions on some stuff? We'll do a couple more examples. All right, why don't you try integral of 2x plus 3 from 0 to 4 dx. See if you can figure that out. All right, I should have paused it, sorry. So do we get the antiderivative? Okay, good question, Carter. He said, forgot how to solve for c. So if we have a definite integral, so from 0 to 4, if it's from a number to another number, you do not need to do a plus c. There's no plus c. If there's no numbers here, that's called an indefinite integral. That's when you do a plus c. All right, so antiderivative. What are we at? X squared plus 3x. And we're going from 0 to 4. So that gives me 16 plus 12 minus 0 plus 0 gives me 28 for an answer. Okay? What we found is the area under the curve of 2x plus 3 from 0 to 4. I'll show you the 5-2 version where we could still do this without antiderivatives using like geometry. It's kind of messy, but it's a trapezoid. 1/2 base 1 plus base 2 times the height, which is 4, and we get 28 doing that. All right. Questions?